There are a variety of diseases that ultimately are of interest. The things I'll talk about today are cancer diagnosis, and especially lung cancer diagnosis. The example that I'll talk about today and show a couple of results from involves a single base mutation on one of the genes that's indicative of lung cancer. It's the KRAS gene, and when it happens, you get a change in one base in your oligonucleotide somewhere in a cell in your lung. And ultimately what develops out of that is a lung cancer, a tumor that metastasizes ultimately and has potentially lethal effects. And so the idea behind cancer diagnostics is obviously you want to involve risk assessment, so who needs to get these tests. And then the key that we're after and what we want to be able to do is really target early diagnosis. So when somebody has a stage 1 lung cancer, all right, the odds of survival are something on the order of 85%. Somebody has stage 2 lung cancer, the odds of survival drop to 13%. The typical survival rate for the lung cancer that we're interested in dealing with is 15% as a 5-year survival rate. All right, even if you're not engineers, stage 1's 85%, stage 2's 13%, the typical is 15%. When does that say everybody's being diagnosed? Stage 2 or later, right? And the reason for that is that it's asymptomatic, as are many cancers, until they get to the point that they've metastasized or caused other problems. So if we want to tackle this disease, we need to be able to diagnose it early with very simple tests. And what that ultimately does is improve prognosis. We also have the potential, especially if we combine antigen screening with DNA screening, to actually not only say that this person has lung cancer, but also what is this person's lung cancer going to be susceptible to? Which chemotherapy agents are actually the best to target that lung cancer and actually treat that person's very specific lung cancer? And we can do that with the type of array testing that's ultimately available. So do basically patient classification and then be able to select a personalized therapy for that. So when we think of tests, and there are a lot of actually fantastic tests out there for doing both antigen detection and oligonucleotide or genetic information detection. And they all combine, if you want to develop something that detects a small number of molecules, they combine two different themes: target amplification and signal amplification. And what I mean by that, first of all, target amplification, because it's probably the most common technology. If I want to be able to detect a molecule of DNA, all right, if I want to be able to detect 1 or 2 molecules of DNA, there are certain very, very expensive techniques down here that'll actually detect a single molecule, whether it's of an antigen or whether it's of an oligonucleotide like DNA. All right, but those tests would be extremely prohibitive, literally tens or hundreds of thousands of dollars to be able to detect that one molecule, require extensive development, etc. Instead, what people have done is say, all right, I need to develop techniques for amplifying that number of molecules of DNA. So I want to take that one molecule of DNA, and especially using DNA's self-replicating ability, I want to make that one molecule of DNA hundreds of thousands or tens of millions of molecules of that exact same molecule of DNA. That's target amplification. That's where you take the molecule you're interested in and you typically enzymatically or by a variety of other means, you replicate it. And that's very possible with polymerase chain reactions or PCR for DNA. And it works very, very nicely. It's a relatively expensive technology. Each of the bases that goes into that is relatively expensive. But it's very, very feasible and has been used extensively. Lots of biochemical techniques have been developed around this to try to get selective amplification. So if you're interested in only a small number of the oligonucleotides in this sea of other DNA molecules, can you make those and selectively amplify those? Techniques like that have been developed and they're actually very, very valuable. All right, so that's target amplification. Signal amplification is, all right, I have a certain number of molecules, how do I detect them? All right, so let's say I somehow make each molecule fluorescent. Well, if I make each molecule fluorescent, the more molecules I have on that surface, the cheaper I can detect those. And I don't have all the slides that go into this, but you can go all the way up to technology that's been developed by Endeavor. This is a local company started out of Kathy Rowland's lab here at the university. Now she's at that company. They're developing both visible light and fluorescent detectors that are very, very capable of detecting a relatively large number of molecules with extremely cheap detectors. And the idea there being that, hey, if I can have something with target amplification that gives me a signal that's relatively high, all right, I might be able to do disease diagnosis on the spot, all right? So to actually do remote applications, say in third world countries, of diseases like SARS or the bird flu, et cetera, and actually be able to do that on site very specifically and very nicely. And the nice thing about that is you can make a detector for detecting large number of signals that might only cost $20, all right? Literally with parts you can buy online for something on that order. If you get down into talking about 1 molecule per micron squared, all right, so you have 1 fluorophore or 1 signaling molecule per square micron, then you're talking about the ability to need something like a fluorescence microarray reader. Now you're talking about an instrument that's all the way up in the $100,000 range, all right, and as you continue to go down, things continue to get more expensive. And so it's really the product of these two that we're interested in. We're going to focus on on signal amplification, but not in a means that actually requires instrumentation or expensive instrumentation. As I said, basically the polymerization event itself is an amplification. So it will take a target and it'll multiply it. And so let's say we're looking at having developed a chip, and I make these to be indicative of whether they're antigen-antibody interactions or whether they're DNA hybridization or oligonucleotide hybridization reactions. The methodologies are very similar. The examples I'll show today are all from hybridization, but it can be extended to antigen-antibody interactions, and we've done that. I just don't have time to talk about the examples of that today. So let's say that I put this surface, and imagine that this is the marker that's indicative of someone having lung cancer, that mutated oligonucleotide sequence. This is the native oligonucleotide sequence. It's one that almost everybody has in their blood. So, or if I do the test right on everybody, I'll get a positive response from here. It's basically a positive control to the test. And now I expose this to somebody's blood who doesn't have lung cancer, right? And I selectively label, and I'll talk briefly about how I do the labeling here in a little bit, or how we do the labeling here in a little bit. I selectively label that antigen, or that, in this case, DNA molecule, with a marker that's going to trigger that initiation reaction. Well, when I do that now, I get specific interactions because of the biochemistry of the system, DNA hybridization. I react and onto the surface here. Now I expose that surface to monomer. That's what is the kind of the substrate for the polymerization reaction. And HNU, which represents the light that causes this initiator molecule to decay into its active species. That forms now a very large amount of polymer, and it only does it where I had the positive signal. So in this case, I see no polymer here, and I actually see polymer here. And the advantage of that polymerization reaction is I don't have to worry about detecting this with a fluorescent microscope or something like that. I actually can see this signal on the surface itself. Since I'm running a little behind, this is basically the details of some of the details of how we would do that. You have 2 different signals on the chip, and it amplifies those steps. You first hybridize, so you get pairing of the oligonucleotides on the surface. In our case, we put biotin on the ends of those oligonucleotides. The biotin-avidin interaction is an antigen-antibody interaction. It's very specific, very strong. We couple that avidin to a photoinitiator that I'll talk about here in a second, and then that photoinitiator in the presence of monomer gives us polymerization. So now we have, for example, colored polymerization if we incorporate a dye or a molecule that fluoresces in there. And in the other, we get no polymerization, so we still have our substrate. So one of the first steps to doing this is to say, all right, we want to make this work and we want to make it as sensitive as possible. Let's not just couple 1 initiator per event. We know each initiator that's on the surface will ultimately lead to the polymerization of a large number of molecules, but let's not couple just 1 initiator to that surface. Let's actually couple, and it turns out, hundreds of initiators to that surface. So we use a big polymer molecule, and that polymer molecule contains the avidin that I talked about in the previous slide, so it'll interact with the biotin. It contains 2 or 3 of those, and it contains hundreds of initiator molecules. So now when I expose the surface to this, for every spot on the surface that I had 1 biotin, I now get 100 initiator molecules, in theory. All right? And so Rob Jennison worked with us to create a dilution chip, and the idea being that we have decreasing numbers of oligonucleotides that have a biotin in group on them on this chip. And so we have 8 different concentrations that decrease the absolute number of biotin molecules on that surface, or biotin moieties on that surface, and then a 9th spot where we just printed oligonucleotides. There's no biotin, so it looks for non-specific interactions and effectively works as the negative control for that chip and that detection system. What you see over here is just a digital camera image of that surface after we take it through all of our processing steps. All right? So you can see we light up between 6 and 7 spots. The 6th spot is definitely lit up, the 7th spot is not. And by lit up, I mean forming enough polymer on that surface that we can actually see it. All right? Turns out that at this spot, they're on the order of, or between those two, they're on the order of 1,000 to 5,000 molecules present in that system. That gives us a detection, and converting this to a macroscopic signal from only 1 biotin molecule for every 20 square microns on that surface. All right? And we can convert that to a signal you literally can see with your naked eye. And this isn't a microscope or anything, it's just a digital camera image of that. So we can take something that's about 1,000 molecules on the surface and we can detect it. So that gives us our qualitative response. One of the things that we're actually very excited about is that we don't only get a qualitative response, we actually have some early indications that we'll actually be able to not only say that someone has a disease, but what level is that disease at? We can actually quantify this. And these were published in Nature Materials earlier this year. But the idea here is that as you increase the number or the light intensity or the time that you expose, more of these spots show up. So say, for example, I only expose for 20 seconds, well, only these 2 spots will show up. If I expose for a minute, maybe the next 3 spots show up. If I expose for 90 seconds, then I get all 6 spots to show up that I'm going to get. And by observing when these spots show up, I actually know how much of the material that I have on the surface. And that gives us the potential ultimately to make this technique quantifiable as well.